Okay, so good afternoon everyone. We are Group 9 and we're excited to present learning efficient variational quantum circuits with state reinforcement learning. And our goal is to minimize the energy of a quantum system while keeping the surface depth low to find more close ground states. In the NISQ era, more qubits and deeper circuits mean more decoherence and higher error rates. We can't extend hardware coherence time, but we can design shallower circuits with fewer 2-qubit gates. PQE follows this principle and making it practical for quantum chemistry and physics. And we all know that PQE is a hybrid quantum classical algorithm. Quantum parts and classical parts have different work in our approach. We replace the classical optimizer with Proximal Policy Optimization, and the parameterized circuit acts as the environment, returning a result based on measured energy. Our PPO agent iteratively updates parameters to find the minimum energy solution. With our method, we achieve energy results within 10 to the power minus 5 of the full configuration interaction benchmark.
So our project strategy, first of all, we start with a set of the parameters quantum parameters, and we execute the PQC to measure the expectation of the Hamiltonians. And we send this result to the critical model of the PPO agent, and the actors will update the policy use this result. And after this work, we will renew the PQC and go this loop again, and to optimize our answer. And through this closed loop workflow, we eventually find PQC parameters that best estimate the molecular ground state and the molecule. In our experiment setup, our molecule that is used the D-therm hydride, and the right side of the slide is the reference learning training parameter, and the down of the slide is the DPO setting of our experiment. And the PQC of our experiment is a 50 times 17 matrix, and the 17 columns is the first 12 is the gate type that we choose in this experiment. It's on the right side of this slide, and the other 5 is the target qubit, control qubit, and goal position, and the connective defects.
Okay, so we have talked about the background and setup of our experiment. So let's work on the reward function that we have designed. Actually, we will focus on the accuracy, that is the differences between the energy, calc energy, and calculated energy. We can see the delta E, and also the depth of the gate of the circuit, and number of gates that you will minimize, and then number of CNOT, that is crucial for the energy gain. And also, if it converges, you have extra, in the end, we have the extra reward. And why we set that high amount of delta E, the rate is high, because we want to minimize the difference to a power of minus 5, 10 to minus 5, so it's around 10 to 5. And the rate is 5, so it matches. So this is the activation function we use. We use the categorical softmax, and we use, because it's a different categories with different gates, so we use the different these functions. It's logical, and then we have some state space. We have mentioned by us the gate types and different control and target for the control gates, and rotation angle for the rotation gates, and the position of the original gate and some connectivity of between qubits. And action space are different types of gates, and how to assign the qubit rotation. Okay. So after all the background we have discussed, so let's move on to promising results. This is one of the trials we have. This is some trial we have tried, and you can see that it is actually the -3 HA here, and it's actually not really attain what we want, the -5. So we want. So that was why we set to 10 to 5, power 5, to the energy difference. It was 10. It was just 10 to 3, and now we're 10 to 5 or 10 to yeah, and it actually converges here. You can see the reward is increasing, the energy decreasing. And after increasing to 10 to the power 5, then you can see that it's actually makes it work. 1 to -5 here. And surprisingly, we can see it's actually very slim. You can see its convergence. You can show the convergence here. Actually, the rotation, you can combine it into one rotation here. So it's a sign of convergence in this circuit. So it's actually very short. And then convergence rate actually is still training up to our submission, but after training we're up to the 10,000 episode, and then it actually converges to a very high reward, very good reward. Okay, so let's move on to quantum implementation.
So we also wanted to, because all of our simulations ran on the simulator, we wanted to try evaluate one of our circuits on a real machine as well. So we took one of the earlier models that we trained. We used it to generate a circuit, and we evaluated that on a real quantum machine. And this is the circuit that we got. It's an 8-layer 42-gate circuit, which could be optimized using the transpiler down to 5 layers and 25 gates, and running on the 2 IBM machines on Strasbourg and Aachen with the Eagle and Hen architectures. We actually got results which are very similar to, or which are relatively similar to what we were seeking, confirming that it is plausible to use this method on the real hardware as well.
Okay, one further add is that for the conclusion, we are actually, apart from achieving all the results, we want to actually improve it by changing the weight of the energy difference, because we just set a constant weight. We may set it a small weight in the beginning, and then make it larger so that it can explore at the beginning, explore more at the beginning, and then make the energy difference high weight so it can converge in the end. So maybe have a better result, probably. So this is the end of our presentation. Thank you.